The main light source is a sun simulator borrowed from Planet X News. It's pretty versatile with a Nibiru attack mode and lunar eclipse option. At the other end of the room, not quite 93 million miles away, we have a comically undersized Earth globe. The small size, together with the sun simulator's distance, produces fairly parallel rays and a sharp terminator line. We also have some ambient starlight to show my random hand waving, which helps explain things to flatards. For astronomers, the equinox is the moment when the plane of the Earth's equator passes through the centre of the Sun's disk. This occurs twice each year around March 20th and September 23rd. For the rest of us, it's an all-day event, where the Earth's axis of rotation is perpendicular to the Sun's incoming rays, and this gives us some special observations. Introducing the terminator line, the point where night meets day and vice versa. The terminator is always at 90 degrees to the Sun's incoming rays. Because the Earth's axis is also at 90 degrees to the Sun on the equinox, all the north-south lines of longitude are aligned with the terminator. Since west is defined as 270 degrees from north, that means as locations cross the terminator line, the Sun has to set due west. Just as the Sun sets in the west on the equinoxes, it rises due east for the same reasons. That really bangs a nail in the flat Earth coffin. Equal day and night is simply the combination of the last 2 points. As the Earth has no effective tilt to the Sun at the equinox, half the planet is getting sunlight. If the terminator line and the lines of longitude are both at 90 degrees to the Sun, then the Sun rises at the same time for all latitudes outside of the poles, and also sets at the same time at all latitudes. In one revolution, we get 180 degrees of daylight and 180 degrees of nighttime. There is one phenomenon that can't be shown on a model. Due to atmospheric refraction, we actually get about 12 minutes more daylight than nighttime at the equinox. It's the one time that flat Earth dirty air comes in handy. That really cuts into the flat Earth theory. Let's pick a latitude of 30 degrees north and draw a line to represent a vertical object on the surface of the Earth. At solar noon, the Sun's rays are coming in at an angle of 30 degrees to the surface. To an observer, the angle of elevation is 60 degrees, making the zenith angle of the Sun 90 degrees minus the latitude, and this works at all latitudes at the equinox. Looking at the Sun's point of view, the equator is a straight line. Objects only cast shadows to the east or west during the equinox, and never north or south, thus showing the Sun is travelling in a straight line over the equator. At solar noon, objects cast no shadow at all, showing the Sun is directly overhead. That puts another hole in the flat Earth model. On a globe, the EQ mount's polar axis has to align with either the northern or southern celestial pole in order for it to cancel out the Earth's rotation. The second axis, declination, allows you to move 180 degrees from horizon to horizon while still countering the Earth's movement through the polar axis. On a flat Earth, even if you have the polar axis aimed at the NCP, objects rising and setting prescribe ovals rather than circles when away from the North Pole. The EQ mount would need 2 drive motors programmed in sync to follow these ovals. In less than 5 minutes, the Equinox and EQ scope mounts have shown that the globe Earth easily explains all the observations we can make. On the other hand, a flat Earth model needs endless special cases, like atmospheric lensing, perspective, dirty air, lampshades, and the list goes on. Even then, the flat Earth model can't explain many observations, and flatards have to ignore them in the end.